Hello, everyone. I am honored to present our work, MarineEval, assessing the marine intelligence of vision-language models, which has been submitted to WACV 2026. This research introduces a comprehensive benchmark specifically engineered to evaluate the performance of vision-language models in solving complex, domain-specific marine questions. We are currently witnessing a golden age of vision-language models. SOTA models like GPT-4o, Gemini, and Quen have demonstrated remarkable capabilities as general-purpose assistants, excelling at open vocabulary recognition, image captioning, and visual question answering. However, as these models transition from general applications into specialized scientific fields like marine science, a critical question arises. Can they truly act as marine domain experts? The marine environment covers 71% of our planet, yet it remains one of the most logistically difficult and expensive areas to observe and collect data. Consequently, annotated data sets and expert documentation are scarce compared to the general domain. While a VLM can easily identify a car on a sunny street, the underwater world is a far more hostile environment for AI. Furthermore, marine visual data is characterized by low contrast, color attenuation, and highly complex habitats. We therefore require a systematic framework to evaluate whether existing VLMs can bridge this domain gap. To address this, we construct a benchmark that systematically evaluates different capabilities of VLMs required to solve marine-specific questions. We have summarized 7 core capabilities. First is species comprehension, which requires both precise taxonomic identification and the interpretation of ecological roles. It encompasses 6 subdimensions, beginning with species identification, requiring models to provide formal scientific name of a species. Cross-image matching determines if models can recognize the same species in varying contexts. Biodiversity recognition requires the identification of common names of all species within a single scene. Beyond simple identification, we also introduce ecological attribute inference to evaluate how well a model matches species to their ecological attribute, such as habitats and distribution. Interspecies relationships asks models to classify trophic interactions, such as predator-prey dynamics, and camouflage localization test models to detect the hidden organisms. Our second dimension is behavior and trait extraction. This capability focuses on deriving granular insights into physical characteristics through morphological trait extraction and identifying temporal actions through the classification of behaviors within video sequences. To ensure robustness, we include hallucination resistance. This tests whether a model is susceptible to being misled by its own training priors. For example, since clownfish and sea anemones are frequently paired in data, we provide images of anemones without clownfish to see if the model incorrectly hallucinates their presence. Our fourth dimension, document interpretation, evaluate the capacity of VLMs to analyze and derive insight from scientific literature and documents. It includes sources from books, journal articles, and scientific figures. Our fifth dimension, conservation and threat analysis, shifts the focus toward environmental stewardship. Here, we assess the model's proficiency in determining the threat status of various species, identifying and localizing pollutants, and classifying environmental disasters depicted in the imagery. Our sixth dimension, spatial reasoning, measures geometric comprehension within the unique optics of the aquatic environment. This involves visual grounding, the precise counting of target species, distance estimation, and the assessment of spatial relations between objects throughout the water column. Finally, we evaluate the model's understanding of marine technology. The model must go beyond simple object recognition to infer the primary functions or scientific contributions of specialized oceanographic instruments. By covering these 7 areas, MarineEval provides a holistic view of a model's specialized domain expertise. Our data collection process involved curating high-quality images and labels from professional platforms like Fishbase and iNaturalist, as well as academic journals, public data set, self-collected field data, and search engine. To ensure the integrity of the benchmark, we implemented a visual necessity test. We filtered out any question-answer pairs that could be answered by a model using text-only cues. As you can see from the table on the right, when the visual input is removed, accuracy drops significantly. This confirms that MarineEval strictly evaluates visual understanding rather than linguistic patterns. All remaining pairs were then verified by domain experts to constitute the final MarineEval dataset. Under the hood, MarineEval consists of 2,000 image-based QA pairs spanning 20 subdimensions. We utilize 5 distinct question formats: yes-no questions, multiple-choice questions, localization questions, closed-form questions, and summarization questions. While yes-no and multiple-choice formats allow for easy scaling, we intentionally retain closed-form and summarization tasks to reflect real-world scientific utility, which constitute to more than 1/4 of the dataset. Compared to existing benchmarks, MarineEval offers a comparable sample size but also with significantly higher question format diversity. Beyond statistics, MarineEval is characterized by its focus on domain-specific knowledge, such as taxonomic granularity and biogeographic distribution. We also explicitly test the models against the domain shift inherent in underwater photography, specifically the low contrast and color attenuation that often confuse general-purpose vision encoders. To ensure our evaluation process is both objective and stable, we have implemented a rigorous scoring pipeline. First, we adopted a binary judgment strategy. This means we classify every model response strictly as either correct or wrong. We chose this over more traditional methods like Likert scale scoring, which require a reviewer to score a response on a numerical range. While common, the problem with Likert scales in AI evaluation is that they are often highly subjective. There is usually no clear, universal definition to quantify the difference between a score of 3 and a score of 4. This lack of precision can introduce significant bias and inconsistency into the final results. To ensure stability when we use LLM as judges for our more complex, close-formed, and summarization questions, we provide them with explicit marking rubrics. These rubrics clearly state the required facts for a correct answer and instruct the model to judge only whether those specific criteria were met. Later in the presentation, we will show data confirming that using LLMs as judges with these rubrics produces highly stable and reliable outputs. We benchmarked 17 SOTA models, including 12 open source and 5 closed source variants. Based on the dashboard at the lower left corner, our results show that the best open source and closed source models are Intern VL3 and Gemini 2.0 Flash Vision, respectively. The remaining dashboard and the bar chart also tell that there is a clear performance hierarchy. Humans with marine background outperform humans with general background, who in turn outperform closed source models, with open source models trailing behind. Crucially, even the best models currently cannot replace a human with general marine knowledge. We also observe that there are 2 challenging tasks for VLMs. Spatial reasoning dimension remains a fundamental limitation of current VLM architectures, which inherits the limitation from general domain. On the other hand, the failure in species comprehension highlight a severe lack of domain-specific training data. The lower right corner shows the reliability of using LLMs as judges. Our experiments demonstrate that the judgments of LLMs achieve around 95% agreement with humans evaluators. LLMs also produce stable judgments because when we repeat the evaluation process 3 times, the standard deviation of accuracy across different trails is negligible. In conclusion, MarineEval contributes the first rigorous benchmark for marine intelligence, a robust evaluation pipeline featuring visual necessity testing, and a clear roadmap of the challenges facing the next generation of VLMs. Moving forward, our goal is to develop a domain-specific training corpus to enhance ecological knowledge and spatial reasoning. We plan to explore architectural improvements that incorporate marine science expertise directly into the model's training loop. The future of marine AI is promising, from automated biodiversity monitoring to conservation assistance. We hope MarineEval serves as the foundational step toward these vital applications. Thank you so much for your attention. If you have any questions, feel free to contact us for discussion.